Most people can calculate an average but have no idea whether that average actually represents the data they are looking at. They think the average is the whole story, that it stands in for a typical value and that everything else is just noise. What actually happens is that different data sets can share the same average while having very different amounts of spread, so errors and surprises pile up even when the center looks stable. Picture promising a client a delivery window based on the average time you have seen so far, not realizing that the same average hides long delays that are about to embarrass you. Start with this. An average is a location, not a guarantee. It is the balancing point of your data on a line, the place where the pulls from the smaller and larger values cancel out. If you only remember that, you will stop treating an average like a promise and start treating it like a coordinate in a landscape. But a coordinate does not tell you how bumpy that landscape is, and that bumpiness is what variance and standard deviation measure. The intuition that the average is typical fails the moment the data have uneven tails or clumps. Imagine two piles of weights on a beam that balance at the same point. One pile is spread out and the other is tightly stacked. They balance at the same location, yet their behavior under a small shove is different. That difference under a shove is the role of spread in data. It determines how often you will be far from the center and how bad your misses can be. Variance is the systematic way to quantify that spread. You start by picking the average as a reference point. Then you look at each value's distance from that reference. You square those distances so that values on opposite sides do not cancel, and so that large misses count more than small ones. Then you average those square distances. That final average is the variance. Standard deviation is just the square root of that variance, which brings the unit back to the scale you care about. If the data are measured in minutes, the standard deviation is also in minutes. That matters because you can talk about it in the same language as the average. A practical read is this. Standard deviation is the typical size of your miss from the average. Not the maximum miss, not the most frequent miss, but a consistent scale of fluctuation that turns a vague sense of variability into a number you can use. Consider two commuting routes with the same average travel time of 20 minutes. On the erratic route, some days take about 5 minutes and others spike toward 50, so the average hides a pattern of calm mornings punctured by big delays. On the steady route, day-to-day times hover close to the average, so you leave at the same moment and arrive at about the same moment. The averages match, but the standard deviations are very different, and that gap is exactly what your schedule feels. If you plan with only the average, you live on a knife edge. You book meetings right after your supposed arrival time, you promise shipping windows that barely fit your plan, and you interpret every late day as bad luck. In reality, the plan is fragile because spread was never accounted for. The late days are predictable consequences of ignoring variance. Adding buffer blindly is not a fix either, because without a measure of spread, you do not know how much buffer to add or when it actually changes the risk. Here is the most common beginner mistake: comparing groups, processes, or models using only their averages and declaring a winner. A sales team looks at average monthly revenue and crowns a strategy that happens to rely on a few giant deals while ignoring that most months drag. An experimenter looks at two treatment averages and forgets that one group varies wildly, so a small observed gap might be drowned by scatter. Mean chasing like this leads to brittle conclusions that fall apart under variability. The practical cost shows up as wrong forecasts, broken service level promises, and models that either overfit or underreact. Capacity planning fails because peaks keep overwhelming the system even though the average load looks fine. Risk analysis misses fat tails that drive losses, so managers get surprised by events that a simple spread calculation would have revealed. On the modeling side, training with features on wildly different scales destabilizes learning because features with larger variation dominate updates. The correction is mechanical and immediate. Always pair an average with a measure of spread and act on it. Compute the standard deviation and say it out loud anytime you report an average. Treat it as part of the name of the data, not an optional footnote. Use it to set buffers, to compare processes for reliability, and to standardize inputs before training a model by subtracting the average and dividing by the standard deviation. If you see the same average with a larger standard deviation, assume more misses, wider prediction intervals, and a need for more samples before you trust any claim. Why do we square the distances when computing variance instead of just taking absolute values? Squaring prevents positive and negative differences from canceling, and it makes large deviations pull harder than small ones, which reflects the reality that extremes are disproportionately costly. It also unlocks clean algebra. When independent sources of variability combine, their variances add, which is not true if you use raw absolute deviations. That additivity is a backbone fact you will use repeatedly without even noticing it. A subtlety matters when you estimate spread from a limited sample rather than from the entire population. If you simply average the squared distances from the sample average, you tend to underestimate the true spread because the sample average is itself pulled toward the sample. Standard practice is to apply a small upward adjustment to that average of squared distances before taking the square root. This is a built-in correction for using a reference point computed from the same data. You do not need to memorize a recipe here. The point is that spread is slightly harder to estimate than a mean and deserves care. Variance and standard deviation also guide modeling hygiene. When features live on different scales, algorithms that rely on distance, dot products, or gradient steps get skewed toward the largest scale feature, even if it is not informative. Standardizing each feature to have 0 average and unit standard deviation levels the playing field so that weights capture signal instead of compensating for units. Regularization penalties that limit effective spread of predictions are, at their core, constraints on variance to prevent overreaction to noise. There's a geometric read that connects to probability. If you think of standard deviation as a scale bar for randomness, then statements about typical ranges become meaningful rather than vague. In bell-shaped data, about 2/3 of values land within one standard deviation of the average, which gives you a quick mental map from spread to credible ranges. That is not a promise for every distribution, but it hints at why the shape of the distribution and the scale of variability interact to produce the patterns you observe. Common pitfalls follow the same pattern. People confuse variance and standard deviation and compare them directly. That is mixing squared units with base units and leads to nonsense conclusions. Others see a small standard deviation and assume a bell shape, then get surprised by rare large misses because the tails were heavier than they assumed. Another mistake is treating a single tidy sample as proof of low spread. Small samples can look calm by accident, and without explicit spread calculations, you have no sense of reliability. Spread is not just a number to file away. It is the bridge from descriptive summaries to decisions under uncertainty. Cutoffs, thresholds, and risk tolerances all rely on how far things wander from the center and how often they do so. Even when you only care about an average effect, the expected error bars and the sample size you need are controlled by variance, not by the mean itself. If you do not measure spread, you have no basis for planning, only hope. In data cleaning and exploratory steps, variance and standard deviation tell you where to look next. Unusually large spread in a feature suggests multiple regimes, a measurement issue, or an outlier process worth isolating. Extremely small spread may indicate a constant that should be dropped, or a constrained field that can be encoded differently. These are straightforward mechanical checks that save you from chasing artifacts as if they were signal. For forecasting and simulation, spread is the input that turns a point estimate into a distribution of possible outcomes. You can simulate scenarios by drawing values around the average using the measured standard deviation as the scale. This shows your plan's sensitivity before you experience it in production. If a downstream metric is a sum of independent components, the variance of the sum is the sum of the variances, which gives you a quick way to size buffers and to understand compounded risk. Again, this comes directly from the way squaring makes variance play nicely under addition. The single shift that matters here is this. Stop treating the average as the fact and variance as trivia, and start treating the average as a location whose meaning is only clear when you also know how far and how often values wander from it. If you instinctively ask for the spread whenever you hear a mean, you will automatically make tighter predictions, set realistic buffers, and pick models that behave under noise. Center tells you where, spread tells you how reliable that where is. Next, we will tackle what a normal distribution actually means and why it shows up everywhere, because you will use it to translate a measured spread into concrete probability statements for the decisions you care about.